Hello, 6th grade. I just wanted to touch base because I know there was some confusion for today's lesson, so I just want to make sure I clarified a few things. And then if you wanted to go back and correct your slides, you may, because I obviously never want you to feel lost, confused, or left alone when you're working on something. So if you look at this first slide, something really important to notice is that sound waves look different than light waves. And the reason that there was supposed to be a demo with a slinky and a demo with a string is because they look different. Sound waves travel in a bunch of particles that travel like compression waves, and their amplitude is in a different spot. It's wherever all those waves are compressed is their amplitude, and the wider that is, that's like the higher the amplitude on light waves. And so amplitude in sound waves looks a lot different than amplitude in light waves. So the reason you were supposed to use the string for one, and the first time you were supposed to use the string, you were supposed to slowly bounce it and just talk about, were the waves tall? Did they reach the door handle quickly? Did they bounce back? Hey, I know most of you are assuming it's supposed to bounce back, but if yours didn't, just tell me what your waves did, because this is science, and I want to hear what you observed, and that's okay. And then you're supposed to do it again, but this time you're supposed to bounce it like crazy fast, like a crazy person, okay? And see, is the amplitude higher this time? Does it get to the doorknob quicker? When it hits the doorknob, does it bounce back this time? If it still doesn't bounce back, still tell me. It doesn't bounce back. That's okay. Here, please make sure that you answer question 1. Which waves do you think represented a bright light and why? And then I want you to draw what the slow-moving wave looked like versus what the vigorous, fast-moving wave looked like. Now, if you want to draw by hand and insert pictures with a Chromebook, great. If you want to draw on Google Drawings, awesome. If you just want to type in a description because you're tired of trying to insert a picture, also okay. Now, I would say most of you got that pretty well because you could do the string. Here's the problem. A lot of you didn't have a slinky, and I get that frustration because I was all stoked to do this demo with you with a slinky on Monday, and then I realized ours was lost and broken. So I want to show you what I was hoping you'd get from this video. And I'm not going to make you watch the whole thing with me.
With a
Here we've got our
transverse wave,
waves.
the particles move up and down.
Transverse
Light
waves
waves move this way.
are light waves.
Slinkies can also make transverse waves.
A lot of us love to use slinkies for light
With
waves,
longitudinal waves, particles are pushed together and pulled apart by vibrating objects, and the energy of the push and pull radiate out. Longitudinal waves, these high-pressure pushes and low-pressure pulls, are what cause sound.
So those longitudinal waves are what I keep calling compression waves, or those pressure waves. And notice the particles are moving differently in those ones, and that's how sound waves are produced.
If you think about the slinky as the air particles and my moving hand as the vibrating object, you can see the high-pressure push move through the slinky when my hand moves forward.
That's
you can
the
also
amplitude.
see the low-pressure pull move through the slinky when my hand moves back.
So I realized that when you watch that video, it's not like it's tied to a door handle, but you were able to see the high pressure wave push through and then eventually for it to pull back, and that was more of a low pressure thing. And so you were able to witness the amplitude moving as a group, and so hopefully you could catch in there what you were supposed to see, what was happening with the slinky. So again, slow moving slinky versus fast moving slinky. So this time when you draw it though, it should look very different, because this time when you draw it, it's not the up and down movement that the light waves have. It's that longitudinal wave where you've got those compression points, and the wider the compression point, the louder the amplitude. So that's kind of what they're going for there. The last question that I think really threw people off is actually probably because it's really simpler than what you would expect. How are humans able to perceive light waves and sound waves? Well, because God blessed us with our senses, and we have eyes that take in waves of light. So the light waves bounce off of solid surfaces, and our eyes have these cones and rods that absorb those waves. Whereas our ears are able to take in the compression waves of the sound waves, and we have these great things called eardrums that literally vibrate. And then our body can take those vibrations through our inner ear fluid and transform that into the sounds that our brains know and love today. So I hope this helped to clear up some confusion to help you feel confident with this assignment. If you ever have questions, please don't hesitate to reach out to me.